Last time we talked about taking the harmonic oscillator from a 1D system to a 2D system so we could figure out like how to fit that and make that work for a diatomic molecule. So we're actually getting out of the point where we have exhausted all the one-dimensional systems that we're looking at. We're going to start moving into two-dimensional and more three-dimensional systems so we can actually talk about an atom. Hooray! To do that, though, we have to use a new coordinate system. The problem becomes you can express things in X, Y, and Z coordinates, but it either becomes really complicated in some cases, or there's a point where you can't actually separate the variables, which is always a bad thing for what we do. Have you guys ever talked about spherical polar coordinates? By a show of hands, how many people remember what these things are? Okay. So instead of expressing a point as X, Y, and Z, if you have a point in space, you can represent it like, let's pretend my armpit's the origin. We could express it in a distance that way, and then an angle in space. So the two angles, phi and phi, I'm going to call that one, and then the distance r. So rather than representing an object's location with Cartesian coordinates, X, Y, and Z, one could elect spherical polar coordinates. R, theta, phi. Okay. There are also Z matrices, which my advisor used to have to use to program things. If you look at a lot of computational chemistry software packages, a lot of them use Cartesian coordinates now, but you can actually define them based upon other coordinate systems. It's advantageous in terms of some computations, but a lot of times the computer will read these things in and convert them to something else, or it's gotten so good at the point where it doesn't really need to do that. But in the past, where computers were insanely slow, you had to plunk things in that way. All right, let's try to represent this graphically. I'm going to use multiple colors, which you probably don't have, but we're going to try to draw a 3D coordinate system. That direction for 3D, what do you want that one to be? I like Z. The one in the plane of the board. Well, X, okay, good, we're in agreement there. The one coming out and back into the board is Y. So if we have some point, let's say it's in the quadrant back here, we have that point out there. We can describe it as a distance from the origin. Wow, that's a great straight line. That's R. Then if we look at the angle between the x-axis and the z-axis, which is along here, That's theta. What color am I missing? And phi is the distance from, or the angle between the x-axis and the y-axis. That would be phi. Okay, so we'll try to represent this point. Actually, we should do the light to there. Do you guys feel like you understand what this 3D representation is trying to show? It is between, it's like this angle between wherever you're sitting in space and the y-axis. Now, a lot of times what's convenient is to turn your coordinate system so most of these things are 0, which we could do. But a lot of times we're going to represent a system that is free to move about these areas. Okay. There are conversions between the two, and you can show this with a lot of trigonometry. I really don't want to do it because you probably spent like a month in Calc 3 doing this, maybe. At least that's when I did it, was in Calc 3. And then I took a course called Mathematical Physics, which was all the mathematics you needed to understand physics. It was a year-long course. It was where I learned all my mathematics. I learned all my mathematics from physicists. I learned all my physics from chemists. I don't know what I learned from my math professors. Sorry, math people, if you're watching. Between the two. So you can show this times sine theta cosine e r sine theta for y times cosine, times sine of phi. And then z is just nice and easy. It's r times cosine theta. Okay, another important point. So put a dot here. Integration. In spherical polar coordinates, we used d tau is just a generic integration set, right? That becomes r squared, times sine theta times dr d phi d theta. That doesn't look like it's made things any better. We have to introduce other terms in here, which seems scary, but I promise you it won't be that bad when we start looking at things. Okay. If we're integrating only over 2 dimensions, then d tau, you drop off this r squared portion and the dr portion, and you're left with that. Okay. If we think about the Hamiltonian, we always have to worry about the kinetic energy operator. What's the kinetic energy operator for a 1D system? Negative h bar squared over what? 2m times, second derivative with respect to x. So we're going to have to consider second derivatives. How many coordinates do we have to take a derivative with respect to if we want to do this in spherical polar coordinates? 3. And what are those 3? Yeah. Yep, these 3 right here. So, with a lot of trig, you can show that gradient, which I really don't want to do. How would the gradient be defined in terms of Cartesian coordinates? We'd have partial with respect to what? X plus partial with respect to what? Yep. Finally. Yeah. See? Oops. Messy. When we go to spherical polar coordinates, we get 1 over r squared, second derivative with respect to r. Oh, I lied. Derivative with respect to r times r squared. Another derivative with respect to r. 1 over r squared sine theta. Integration with respect to theta. Sine theta, another derivative with respect to theta, plus 1 over r squared sine theta, sine squared theta, geez. Ugh. This is why quantum gets a bad rap. This eraser is terrible. A completely clean board, and I just... Okay. Yep, sine squared theta, second derivative with respect to phi. Okay. If we're only talking about a 2D system, how would this change? So let's look at it in terms of Cartesian coordinates. If we only have 2D, what have we done in the past? So for this section, what would we just get rid of? Yeah, let's get rid of z. So get partial x squared plus partial with respect to y. Okay. Now, when we look at this other guy, there's a lot of complicated stuff that honestly we don't like. What we're going to get rid of is we're going to get rid of the theta terms because they show up a bunch of spots. I hate trigonomic functions, so that's the thing we're going to get rid of. If you look at a 2D system, you get 1 over r. Oh, I'm sorry. Second derivative with respect to r. 1 over r, derivative of r. 1 over r squared. Second derivative with respect to phi. So reducing our dimensionality makes our derivatives way simpler. Okay, so if you don't remember some of these things, try to look back, check out the mathematical section in your book about spherical polar coordinates, just to get an idea of what they represent. Okay, we're going to be using these a lot as we move through. We're going to find ways that this becomes way more simplified. But just keep these ideas in mind as we trickle through the next couple model systems. Are there any questions about this stuff? Okay. You don't necessarily have to know where this all comes from, but just be sure that you can use it.